I'm waiting for a few more people. Today is Saturday. Guessing we thought there will be more students. It looks like it's kind of even empty.
Here.
I don't know. So is there a reason why we are not here? No? They were coming religiously all the days when there are classes. So, whereas thought today no classes, right? On Saturdays, there will be no people. But, and we only need 2 hours. We are not. We don't have anything in the afternoon today. Holy is coming. Yeah, when is Holy? 14. But that's next week. Huh? They leave, but how about classes? Because, yeah, I thought it was 14 Friday, but that's fine. It's not this week. As Sir said, there may be more students today. It looks like not having. So in the meantime, let me ask you any questions. And one thing I would mention also when everybody's here, but the MATLAB code, I know yesterday he was asking a question. I mentioned that the code was given maybe to assist. So it's always good that you understand the code before you make changes to it. What I mean is, I know one of the questions was, well, if you change the dimensions, this doesn't work. Yeah, possibly there is something else in the code that is probably causing that, something happening, right? There was an error. So I don't think that I can answer all the questions in the code because this was written by someone and it was done somewhere like 2012, 13, it's more than 13 years ago. So there is no way that we would remember. Only thing was why we gave that code was so you can run it and see the same results or similar results. Then you can break the code down and understand how it's being written, so that when you make changes to it, you learn from it and then you basically update the code the way you want it, right? It's like some questions they were asking was, why is there so many different MATLAB M files? Mainly because everything is split into smaller subroutines. So these are some people's style, the way that people write, right? So the same way, I think it's not possible for all of us to essentially debug someone else's code. It's going to take hours, to go through. That is right. That is right. You will be able to get it, yeah. So that's what he was trying to, I think, finding an easy solution, but that's probably not going to happen. Yeah. So like what you did, you padded and it worked. But that's the way. But I know he was asking, why can't I do it by 6 by 6 or whatever? Yeah, 8 cross you are working like. No, but he has a point. He has a point too. But the thing what I was mentioning was that the MATLAB code, you could do it, like you can make it customized to a particular system, right? That's what normally we do. Right. I think so. I think that's what I would suggest. To answer your question yesterday about that, the dimension, what I was discussing is still, I know there are still a lot of students missing. So in the meantime, I just asking, the question you asked, I was just telling them that the MATLAB code was provided to assist, right? So that you see how it was done. But there were so many things that even I don't know, because this was written by a student of mine, not a student. And it's been over 14 years. See? So, and I think we provided that as part of the book so that students can, whoever using the book, they can run the code and see, but then they have to go through the math and then fix like if you change the system, right, then you basically might have to change something in that. Remember you were asking what is that particular variable? Yeah. And those kind of things I think is very hard for us within short time. That's what you were saying. I would encourage you to run it, but then after this you understand like what was how it is written, and then you compare it with the slides in terms of the dimension. Then you see, okay, if I'm changing the dimension of the system, what changes do I need in the code? That's one way. The other way is you can actually draft your own MATLAB. I think that's what I would encourage. Because remember, let's say you are going to a job or anywhere, you have to go from the scratch. Nobody is going to provide you with the code, honestly. So that's always going to be there. Okay? So that's number one. And we'll see today, without recording, I will show you some hardware. Some example of real, like remember I said, the autonomous truck or vehicle. And we'll talk about some other things on the automotive control also, on a lab level robot, formation control. So I'll show you some videos. I thought I'd bring it in. I know I was originally waiting, but I will also show that the last day. Since we're ahead, I thought, okay, I'll come. I used the first half. I didn't know most people don't show up, I thought everybody, the way I understood was everybody's going to be here, especially today you guys don't have classes. So, first half I will finish up that nonlinear control system. And then the second half I thought maybe after the tea, play some videos and, so you can see anything I teach, everything is hardware implemented. And, unless it's last 2-3 year old stuff that we are developing in the, but everything else is usually implemented, yeah. It depends. We have used variety. Like I'll mention that today. So some applications we were 8085, 8086, and some we have gone. We thought we need more powerful processor for neural network. Engine emission control. That's a really nice one. We put on multiple engines without changing the structure of the controller except a small minor changes. There I used. Oh yeah, sure. We have used Raspberry. Yeah. So, but Raspberry Pi is probably more powerful. You'll be surprised. We may not even need that. See? You think that, you think neural network, remember we talked about 3 neural networks? You may not need 3 neural networks. You'll be surprised. And I'll show you one of those mobile robots. It's an 8086 processor. So I think sometimes, and then engine we thought, we need a lot, and we did some study, I don't have in the slides, but where we increased the number of neurons and we wanted to see how much time it takes. Hardly it took any time in choosing those ways. So there we used, I think, what is that, not not the Intel based. This other one, not coming, but we use that processor, which is more powerful. It's a 900 megahertz crystal. And we realized that we were not even using 10-15% of the processing. Yeah, you could. Based on the number of multiplications. Remember in the flowchart? You take the, that's how we do it. You take the flowchart, you know the size of the matrix. See, that's why it is needed. Once you know the MATLAB code, you know the size of those matrices. You compute how many multiplications and additions you need. You see, that's all you need. And you, how many nonlinear operations you need, right? Then what you do is each processor, essentially they'll give you a table. Oh yeah, they'll give you a table like how many flops per second, or what is the time it takes to have one addition, one multiplication. Yeah. So you can compute the time. You see? Yeah. Yeah. So I think you could definitely. So in the discrete time book, I don't think this book has some, maybe I don't remember, but the discrete time book has a chapter on engine control. The whole chapter with some not MATLAB C code in there as well. But we don't want to put the code because it takes a lot of pages. So we had some code in one of our books in '98, neural network book, but that wasn't continuous time. Only we give a few lines MATLAB code, But then what happened? We realized the book was getting bulkier, and the cost would go up. So we cut all this, and then we were using, providing this. That's why the MATLAB code was provided as a way to assist, not to part of that book as well. So okay. So just wanted to let you know. Any other questions? So do you know why there are not many people today? Because we thought there were more students. Huh? Today is the day of faculty are here.
No, they know everything.
Yeah, that's right. It's us who have to learn. Right.
We don't know anything.
Anyway, all right. So I'm going to start. I think I brought that laptop just for a few videos. I thought I would just show, but maybe some people will show up at 11 or something.
They will join.
Because yesterday, yesterday, all right. So, any other questions? So that's why I kind of gives you a heads up. Don't expect that you would understand the code because hardly, we didn't go through it. And you may want to, just like I said, put some commands to display, let's print intermediate stuff in there so that you understand what is being done in that part of the code. And in the same way, those subroutines that were separated out. And Sar went through a few, right? Remember, he was going through. But the tutorials, then it will eat away. It won't have, you won't be able to go beyond one program. And second, we really don't want to teach MATLAB code. That's not the goal, essentially. You see? So that's the main reason, okay? Any other questions? And anything we cover? So you guys are continue to spend time working. At least what I suggest is you run the MATLAB code as it is. See if it matches or close enough with the results that we were talking about. Understand that first. Then you go into the MATLAB code and see how or where these are coming out, How is it done? Then you understand that, okay, for that problem, this is how it's done, the dimensions are this, and then you can go back and adjust whatever you want to do, Okay? All right. So I think we are lecture number 8. So we are one lecture ahead. I think that's what I wanted to let you know. So in the last class, if you remember, mainly we are talking about these delays in packet losses. So in this chapter, we won't deal with quantizer. But you can have a quantizer, right? You can do a quantizer also. But here, what we are only dealing with is a nonlinear system, and we are only dealing with delays in packet losses. Yeah. Okay, so and then you have, or you could actually use the output and construct an argument vector. If you're using the output, it's called input-output system. You see that? But it has its own nonlinearity, F and G. If you're using the state, you also have another H and M, nonlinearity. So they're all the same, only difference is, okay? So then this part is standard. We define the value function. We use the Bellman equation here. You see that? This is the Bellman equation. This equation is the Bellman equation, a recursive equation. But we have this, since we have the packet losses and delays, we are using the stochastic domain, expected value. And then basically you do the dynamic programming, right? So last time we went through this part with an identifier. All this we have covered, okay? And then we showed SAR actually gave you some papers. Remember that? The papers essentially give you maybe a little more details in there, okay? So I would encourage you. I normally don't want to put the papers because sometimes it could be more compact, but it looks like there may be more information in the papers, than in the slides. I just made it so that you can finish it off within that 2-hour lectures. Okay? So I think, and I also want you to focus this. You look at that in the proof. Not only you are showing boundedness, you see that here, this cap here, essentially showing that here is my optimal control value. Here is my actual control value. I'm showing that the expected value over time between the difference of this is going to be bounded by a bound du. And du is a small. So what we are trying to prove, this is a finite horizon. What we are trying to prove is the error between that actual control input and the optimal control input is be very close. Now why is it not exact? Why is it not exact? Why is it not converging to that U star in this case? Why? And don't feel bad, don't feel shy. You can guess, why is it not, we're only showing a bounded. See here also, we also showing here also it's bounded in the mean, but we are not showing asymptotically stable or, we're not showing that UK hat converges to UK star. Why? So what is that causing that bounded result, not asymptotic here? In this equation, for example, look at this equation. What is causing that not asymptotic? We need to talk louder. There's fans running here. So what is that? What is that? You will never be able to show asymptotically stable unless this particular term becomes 0. This is nonlinear update law, but that has nothing to do with update law, nonlinear or linear. But there is a term in the nonlinear term rather than converging asymptotically to 0. So if it converges to 0, that means, UK hat goes to UK star, right? The optimum. But here it's reaching close, therefore we are claiming it's bounded in the mean. So what is that in this equation that's causing, or if you go to the next equation, we go into, let's say, in this equation, for example. So what is that? That term that is making it non-zero.
Taking expected value.
Huh? It's an expected value, but that won't be, but there is some other thing. So what is, in this equation, what is the term that is non-zero? So the first term is what? The first term is basically approximating the bulk of the value function, right? So this is a neural network, output WB weights multiplied by the basis function, right? And what is this term? What is that? So what is that term? So those who know, how many of you know neural networks? A little bit. You know neural network, right? So what is that term? Right, why? That's my question. You will be able to, but what is that term? Usually pops up in neural networks. So the target is there and this is actual. This is a target value, right? W. That W is the target weights. You see? So what is this term called? Who else know? Who else has taken a neural network class? Other than her. Is there anybody else? Probably not. So this term we normally called as an approximation error. So this is the output of the neural network. So a neural network equation. Okay. So let me see my cursor here. Okay. So f of x. So if you are trying to approximate a function using the neural network, is basically the W transpose phi, okay, phi of x plus epsilon. So this epsilon is called approximation error or reconstruction error. Okay, approximation error. So the way you can drive that error to zero, if it's a single layer network, you have to have your neurons in a hidden layer, infinite number of neurons. So that means that as you increase the number of neurons, keep going to infinity, that error value keeps decreasing to zero. Is it practical to have infinite neurons? No. So that's why you always have some error in it. You got it? So if it's a multi-layer network, that epsilon value will be smaller than a single layer. But a multi-layer network, you have more variables, like you can increase the number of layers, you can increase the number of neurons per layer. So all that stuff you can do. You see what I'm trying to say? So that epsilon is error. You will not be able to drive that error to zero, but you can make that error as small as you want. So since that error is non-zero, usually in every proof you only show it's bounded in the mean. Don't forget that. Okay? Any questions here? I know that's a quick entire course in neural networks in about 10 minutes. Okay? A 10-minute explanation of a neural network. It's pretty fast today. So that's basically what it is, okay? So you always see, that's why we always say that bounded in the mean or boundedness, because always when you use neural networks, you always have some error. It's called reconstruction error because it's trying to approximate the function f of x. Remember in Q-learning you're approximating A and B? They're the same thing. And here you're approximating f and g. Remember the capital F, AZK, like we have ZK and whatever. So that's what you're doing. Okay? So I would encourage you, if you're a student, remember I told you, I would encourage you to take a class on neural networks. Don't leave, because these are skills needed. If you go, you'll be outdated. Or you may have to take a PhD, either here or email it to me, if you're interested in a PhD. Remember I said that? Yeah, so I think it's important that you need to have the skill. Things are so changing now. In fact, every curriculum in Everywhere is being updated. Yeah. And it's not going to be going away. In fact, I have been to other campus, some other ones in IITs. They do have a course on, they call either computation intelligence or machine learning course, which basically teaches a little bit on neural network, fuzzy logic, evolutionary computation, something like that, to give you the background. Probably like 4th semester or something like that. So I think it's necessary. Remember that. Okay. So this is clear. So we show the mathematically that it's bounded, right? That's what we did. And the same thing here too. We are claiming it's bounded here, and we show this is bounded. And that bound is a small, and it depends on so many factors. One is you can increase the number of neurons. You can also, essentially, there are some other parameters you can adjust to make it smaller. Okay? But it won't be 0. I want you to understand that. It won't be 0. Whereas for linear system, you can do 0. But for non-linear system, you can always have some error. Okay? Any other questions? So this is what we did last class. Flowchart, we went through this example. Okay, I want you to go through this example. And then let's do the nonlinear stuff. Okay, so we talked about the heuristic dynamic programming. This is a method which uses the policy and value iteration. So it's called HDI. And I'm going to look for paper. I asked, I have no access to Google. So I'm asking one of my students to send me one of the papers so I can pass it to you. So this approach called heuristic dynamic programming uses a value iteration, a different approach to solve the same thing. And there are some problems like I mentioned in this approach, but we're going to use this to compare our approach, to compare. This is more like an offline approach. This has got an iteration-based approach. Okay, so we're going to compare ours. So now what we're going to do is, so we would now use a different system in terms of the output. So what I'm trying to do is, this is for infinite horizon. So you see that the cost going up to infinity. The other one we did with n minus k. Okay, so that's a finite time. So since we don't know f and g, first step is to use an identifier, right? We talked about it. So we are using an identifier, and you remember that we have a big neural network. So we have one neural network to identify both f and g, and then we define an identification error in terms of the output. This is the estimated value of the output. This is the actual value, your measured value. You are taking the difference, and then you are coming up with an update. And we talked about this. It's very similar to what I presented, and you need the inverse of this matrix. So in order to have the inverse of this matrix, remember we take the history here. And why do you need the history? History, but what condition it has to satisfy? PE condition, don't forget that. What is PE stands for? Persistency of excitation, don't forget that. Persistency of excitation. Okay? That condition essentially ensures that one is by using those history, you are able to see what is in the black box, which is needed for identification. So identification is trying to understand something is in the black box. That's why we call identification. So in order to do that successfully, we have to have that matrix invertible, and the only way we get invertible is that signal has to be input, has to be persistently exciting, and the input signal is here is U bar. You see that U bar here? The U bar signal has to be the input here, U bar. This signal has to be persistently exciting. And that's why you take all the history here, you see that? Okay, there's a meaning with it, there's a reason, there's a meaning to it. Okay, so that's the identifier, because we need the identifier, so we are using one big neural network to do that. Then, just like we did before, we are now using a value function. Since we are using the Bellman and adaptive dynamic programming and reinforcement learning, So we are using the same idea that we have been talking over and over again. So we have the approximating a value function. Now look at that. Since we are approximating, there is an error in approximation. You see that? There is an error in approximation. And the same thing, you are approximating the control input. Because in control input you know the G. You need to know the G, and G is also unknown, right? Remember that. Both F and G are unknown. Just like your Q learning, we did AZK, BZK. Here FZK and GZK. So since that's unknown, we are using another neural network here. If you see here, we are using another neural network. And you see that there is an error in approximation. You see that? So whenever you are using a neural network, you should have an error in approximation. How about the previous example? See this, there is an error in approximation. Identify. Any questions there? Any questions? So you see that whenever I'm using a neural network, there is always going to be an error. Just like we claim that when you are using a processor, there is a round-off error, right? Remember that? The same thing. We have to use this neural network. That error, you cannot make it zero. Theoretically, we can show infinite number of neurons and infinite number of layers, but always there will be a small error. You can make it small, but you may not be able to make it zero.
So one thing, F and G both are linear and non-linear.
That is correct. Okay. Let me go back to that slide. Yeah, it's non-linear. Go ahead.
Sir, why I am just surprised that any properties of that F and G, even though you are not knowing it perfectly, but any properties of F and G is not required, that is not coming. Other than this, you are assuming something error.
Right. I think there are properties that you are required, and not required is I don't know whether you can find something like that. But I can tell you what is required. One is both this F and G. You see that F and capital G, right? And that's a function of the output, because that's how I'm modeling it in terms of the output. Just to show you, the first half I did the finite horizon, it has a state. The second half, which I'm doing the infinite horizon, I'm doing with respect to output. Just to show you that you asked this question earlier, we could do model it. But once you incorporate the delays and packet losses, that's the equation number 3. Right? So even though you incorporate it in the stochastic domain, it still has to satisfy the Lipschitz continuous property. You have a capital F and G. That is correct. Because that's where, in that transformation only, you are designing the control input. And it has to be controllable and observable. Now remember, we have shown in the chapter 1 that if the original system is controllable and observable.
No, that is okay, but if it is Lipschitz continuous, then there should be some kind of K which should appear.
That's right. That K is that comes in the bound. As a bound. That is correct. So when you do the proof,
the
stability proof, that is correct.
That stability proof
that
should appear.
That's right. It is there. It is there, but I'm not showing all the details, but it's there. It's in the part of the bound that you will get. Because you take the norms, when you are doing the proof, you are bringing in the target weights. That's where you get, and it's bundled into that error, but it should be there. That K has to be there. That Lipschitz constant. Yeah. So that's why I said I can't tell you what is not needed, but I can tell you what is needed.
And this is sufficient.
This is sufficient. That is
sufficient.
That is
Sir, I have one question. I am not able to understand. First problem, you are using ZK,
right.
where state and previous input.
That's right. Just to show you that you can design a controller using the measured state, or you could actually transform the system in terms of the output. Let's say your outputs are measured. Then that is the second, that yk of 0. Remember that?
But when you use y of k,
right,
then that u of k minus q r, that is computed based on output information.
That is correct. It's a computer using the output.
But is it possible to stabilize a system only based on output information?
Yeah. As long as it's observable.
Observe.
As long as it's observable, you can do. That's why I said, the professor, when he asked me, I said controllable and observable. So observability has to be there, exactly. So if it's not observable, you may not be able to do. But if you have that property, observability along with controllability, then you can do with the outputs. Yeah. So the only thing is the C matrix is invertible. Remember that?
Okay.
The C has to be invertible in this case. Because y equal to Cx. So you expect that C is invertible so that it is one-to-one map. Because you need the C as part of that capital F and capital G when you are doing it.
But generally C is a non-square matrix that you schedule.
Right, you can still do it like I showed you with the observer design, like the last time. There the C is not a matrix, invertible. So I did that C plus the pseudo inverse. And look at the slides, I think the professor was asking, that's a good question. If you remember the linear thing that I did in the previous, there was a case where we were using the output feedback. And in that output feedback, the C, I was using C, not a square matrix like here. So there, that's why I did that, like different slides, so that you see the different cases. There, the C is a vector. So if we take the C transpose, to make a matrix, and we take a pseudo inverse. So take a look at it. That's why I keep saying that. Go through the slides that have been provided to you. Got it? Yeah. So I think the course does a very good job in terms of, it was planned by both of us. It was so that it has different cases in there. So you can see that what is needed, and so that you can, it will be complete. Yeah. So take a look at it. Okay? Any other questions before I move on? Okay. So basically that's what we're claiming. Since this is unknown, therefore these dynamics are unknown, and therefore we are using the neural network because we don't have precisely the dynamics, and mainly because of packet losses and delays which are coming out from the network. Okay, so let's go back. If no other questions, at least I'm happy we covered the approximation stuff here. Okay, so then what you do, now here, from here onwards, we are using the reinforcement learning. So if you remember, we are basically writing this error, the residual error or Bellman error. We are taking the V and then we are moving it to the right hand side. This is the temporal difference. You can see that V of y of k plus 1 minus V of y of k. So, and we are equating this equation to an error because since we are using a neural network. So this is k to k plus 1 and this is k plus 1 to infinity. So this is a recursive equation. You see that always you see that. Okay? And so this error is the Bellman error. And ideally, or Hamiltonian, ideally this error should be 0 when it becomes optimal. Got it? It has to be 0 when it becomes optimal. Now, remember that concept we did in high school math when you are trying to find minima and maxima, what you do, you take the derivative equal to 0, right? Remember that? The same thing. The same thing. So then what you are saying is now we are writing this term here, V and all that, based on these update weights, we are writing that in terms of the actual weights. So this term V minus this will be W hat Vk, difference between the time difference between the bases, between this time and that time, that's given by this delta. The delta gives you the difference. So this is time to go, or cost to go from k to k plus 1, and this term providing you in terms of the weights from k plus 1 to infinity. Okay? Now we need to come up with a weight update law for the critique. We need a weight update law. So now we use the same type of weight update law we call gradient descent. So here W hat of k minus alpha V times this. Now remember I told you this value is always going to be less than 1. Remember A over A square plus 1. And there's a reason we did that, but nonlinear control, if you've taken a course, there was a proof that shows that if you are using normalized, this is called normalized update law. This is mainly to make sure that the convergence and the stability working, okay? But the disadvantage of that update law is that it makes the convergence a little bit slow. So in nonlinear control, people don't like that. So keep this in mind. So, but there are other ways to do it, but it's very difficult. Proofs are very difficult. That's why we have to do that. Now look at that. This update law is driven by the Bellman error. So, and then you know, this EVK, you put that expression and you get that expression, and that's equation number 10. So we know these quantities, and you drive that, and then you are constantly tuning the weights of that critique network. Any questions? Any questions?
So, if you tell about the gradient descent.
Okay, so the gradient descent, what it means is it's like a hill, right? Let me see, okay. So let's say hill. So you have a hill, and you really want to come to the bottom of the hill. That's where you really want to converge. And you are somewhere here. And normally we teach this in neural networks and other stuff. So you start here. There are two things that makes in order to reach this. Okay, what are the two things? One is how big is the step you take. Okay, how big is the step, right? The second is the direction of travel. You can go in the opposite direction. If you are taking the opposite direction, can you reach the bottom of the hill? No. Okay, so in order to do that, it's also equally important how big is the step size. Why is that? Let's say you reach here and your step size is big. So what will happen? Once you reach here, instead of reaching to this point, you may just go to here. And then you want to reach here, then you go back here. So how do we know that we take the gradient, the derivative, and the derivative becomes negative? That means you are decreasing. And then if you switch to the other side, it becomes positive. Then you know that you overshoot that. So that's why it's called gradient based. You take the derivative, so you take a cost function, e square or something, and then you take partial e square over partial w. That's what that operation is called gradient. And it assumes like you're going down with a minus sign. It has to decrease. That's a very simple explanation and that's why you get a minus sign. Okay? And you have a constant, it's proportional to the gradient. You put the constant is alpha v, which is the learning rate. And the learning rate is the size of the step. How big is your step you are taking? You see what I'm saying? Any other questions?
Sir, in case of normal, in case of optimization, gradient based method, so in that case the update is that xk plus 1 is what you have written xk plus 1, xk minus that alpha into, but derivative of the fx,
right.
F of function of x.
Right.
Here the
E square. Here is the Bellman square. So you're trying to minimize the Bellman square. So what you do is you take half.
And this is Bellman square and then half.
Yeah, half of that. Yeah, then you take the gradient of it. Because you want to minimize that Bellman error to 0. Fair enough? So it has meaning behind it. That's what I'm skipping it because I don't know whether we'll have time. So any questions? I think that was a very good question. I didn't cover this because some of you don't have the background. And so it probably, it takes a long time, but this is a very simple explanation. The more details are in there in the paper that Prasad has sent you. Look at that paper, it gives you. But as I said, you've got to have a neural network class to understand, like optimization. This is all typically covered. Like what is a gradient descent, Yeah. And you always take a quadratic function. You take the derivative with respect to the weights. That's why you're getting that equation there. And the goal is that you want to minimize it and you reach the bottom of that hill. Okay? Any other questions? Any other questions? Okay. So remember I said there are so many courses is included here, and it's not possible to cover all of them in that short 2 weeks. We were thinking maybe we should add in 1 week today, but in 1 week would have been even worse. Yeah, so maybe it's 2 weeks is kind of an idea. Yeah. As long as there is some happiness from you guys, thinking that it's what I know many of you came leaving the classes, right? So I think, yeah, that's 2 weeks is a long time if you are missing classes. So, okay? All right. Any other questions here before I go? Next slide. No. All right. So the same thing we do for actor design. So the actor design, that's the next thing. We did the critique. So the actor design is basically you're approximating it by the one single neural network, and that's because you need the G. You need the capital G in this case, and since we don't know it, so therefore we are approximating it, and we need to find a way to tune these weights of the actor. And so you see that since we don't have the G, we are replacing that G by the G hat from the identifier. So we are computing the optimal control input by 2 different ways, and we are subtracting it because they are both supposed to be equal. And since we don't have any measured quantity, this is the best way to show. So this is the output of that minus of this, that would give you the plus here, and that is basically what we call control input error. So this term is called control input error. Okay, control input error. So this is the measured quantity. So we use this quantity to tune the weights of the actor, and we use the same gradient descent. Okay, so now with this we can show the proof. The proof is in the paper, and so via Lyapunov method performed UUB. Remember I said UUB can be obtained, identifier, everything. And I think in the proof, I want to show you a little bit in the proof. Since we have not covered, I have this slide, and you see that you need to first select the initial controller to be admissible. And, you can pick here stabilizing control policy. I would basically make it admissible. So this should be admissible control policy. You use these weight update laws, and these are the constants. And you claim that identification error, output error, weight estimation errors of the critique, actor, everything is UUB. And look at the Lyapunov function. So Lyapunov function is a quadratic in the output, and identification error. Okay. So there is an identification error. There is the value function, weight estimation error, Bellman error. Then you have the critique error, and this is the identification. So everything is included. Everything is included. And then what do? You take the first difference. In continuous time, we take the derivative of the Lyapunov function. In discrete time, you take the first difference. Okay? And then you manipulate everything and you show that delta V is less than. Okay, you see that you have some positive constant times k square. Sir, you see this k? Yeah. You can miss it. You can miss it. So here is the learning rates. This is how Sir also was showing you last class that how the learning rates are, there are some bounds. Remember that in the paper? So those are, we use those because we need that delta L has to be less than or equal to 0 for our, so therefore we show that K has to be less than half, all that alpha C square has to be less than 1 because this has to be positive with a minus sign. This is always positive, therefore with the minus sign this is always negative. And that shows that you are decreasing, delta L is decreasing. So all this stuff comes out of the math and you get a constant. This constant is all the approximation errors. And from there, see if this constant is 0, most likely you can show asymptotically stable.
Since this in the mean square, since this constant is non-zero, we can only show boundedness to the mean. Okay? Any questions here? Any questions? The one before? Yeah. So LDN is basically error in the output. We just gave a name, you know. LUN is the weight estimation error of the control. LVN is the weight estimation error of the value function geometry. LCN is basically the error for the, I think this is the identification, my gut feeling is, okay? So you see that this error is the critique weights. So this is basically combination of those two. Yeah, I don't know, maybe let's see here. What is that? What is the identification error? We use some identification. CK, yeah, that's identification. You see? So basically we have to include everything. And you have to make it a quadratic, and then you are showing that everything is bounded. The whole closed loop system is bounded. Okay? Any other questions, guys? Any other questions? So you see that how the bounds come in, and I showed you why it is UUV, not zero. Okay. So any questions? So we are not showing anywhere any other math equation. So I won't show you any more proofs. This is the last one I'm going to show you because we won't have time to show you. But remember, I only showed you the last step. The details of the proof is in the book, or in the papers. Papers sometimes may not have a little more details. The book might have a little more details. Okay? Any other questions? Okay, so let's see if this makes sense. So here are bounds. From there, I was showing that the error in the output is bounded, the identifier weights are bounded, the value function weights are bounded, the control input neural network weights are bounded, and the output is bounded. So all this is bounded, and basically we show that it's bounded in the mean, so basically everything is bounded. So here is a flowchart, and there are two flowcharts. On the left hand side is the HDP VI. Here is an offline process. You do the control policy. You start with some initial value, and then you have the control policy update, control input error, value function using least squares, and then you compare it, and then if it's not, I equal to I plus 1. So here you are making k equal to 0 or k equal to 1, and then you do that, you iterate it. Once you iterate it and this happens, then as you are coming out here, if it's yes, then you have another loop, k equal to k plus 1. And then that loop goes back here. Okay? So 1 is the time, k is the time, I is the iteration. So remember I told you, you hold the time in a sampling interval, you iterate it till it converges. Then once it converges, then you increment the time, k equal to k plus 1. And then again you go back and do the iterations. Within the sampling instant. That's right, that's what I showed you. That's the drawback. Remember I showed you what happens when you can do that, because nobody can tell you how many iterations you need within a sampling interval. And that depends on the nonlinear system. There are so many different factors. No, same. Yeah. Same. So this is on the other hand, look at this second flow chart. This is the current flow chart that we derived. You initialize it, you initialize the control input to an admissible control input. You first define the identifier, then you define the update loss for the identifier. Then you are looking at the value function, critique update law. Then you are looking at the control input, which is the action network, and the actual control policy. and then the control input error to tune the weights, and then here there's no iteration, so k becomes k plus 1 and you keep going back. You see? Any other questions here? Any other questions? Okay. So here is an example. So this is an example of a nonlinear system. It's an affine system, y equal to cx. You see c is known, and maybe this is invertible, probably. 2 minus 1 is 1, yeah. That's invertible. So here is an f of x, this is g of x. We updated it with all the packet losses and everything, and you end up in getting this is f, this is g. And here is the history. So sampling interval is ts equal to 0.1 second. The delay bound is choose random delay. E of tau is this. Bernoulli distribution with e equal to 0.1. Here identifier critique and action updated at each sampling interval, like I said. So now we started with HDP, the heuristic dynamic programming value iteration. Now look at that. If I'm using 100 samples, 100 iterations per sampling instant, nicely stuff converge. Okay? Now what happens when I'm using 10? What happens here? It blows up. Okay? And it blows up because in the numerical iterations, it's not converged. So if you stop the numerical iterations halfway through, it won't converge. Instead of converging, it blows up. It's not even bounded. Okay? Now, so the next step is the effect of delays and packet losses. So here, we are implementing a stable controller. We found a stable controller from this, my paper. Okay, and here we don't, the controller doesn't know the delays and packet losses. It's an affine controller. For affine system continuous time, it doesn't know the delays and packet losses. So I try to see whether what will happen. What happened here? What happened here? It blows up. So what does it tell us? It tells us that delays and packet losses can cause instability, even though that particular controller is able to stabilize it, the nonlinear system, without delays and packet losses. You understand the difference now? So we are taking one at a time, and we are trying to show that. Okay? So now if I know the wireless imperfections, and if I don't, since I don't know, now I'm using in figure 9, now we are using our method we developed, and nicely shows that it converges perfectly. Okay? So what we are claiming is wireless imperfections affect the system stability. Okay? And we also plotted the critique action neural network weights, and you can see after a few seconds, basically these weights converge, the control input converges, and like I told you, initially, okay, so initially there is a slight overshoot observed at the beginning of the figure, and it's due to the initial online learning needed to tune the critique action network and optimal control. So that's why you see there is a spike while the neural network is trying to figure out. So since we are initializing it to 0 or some random value, it's basically trying to learn, right? Remember that. And that's why you see a spike and quickly learns it. Once it learns it, then things get pretty good, right? It converges. Okay? Here is the flowchart. The same thing we did, control input, update loss for the identifier, the Bellman error, residual error, critique update law, and then goes back. Okay? Another example. This is a different example. Here, look at that C matrix. The C matrix is different, right? You saw that? And this is invertible. It's C is not invertible? Yeah, it is invertible, right? So C is invertible. This is a different system, and here the TS sampling time is 100 milliseconds. Delay bound is set as 2, D bar is 2. Mean random delay values are 80 milliseconds. E tau is 150 milliseconds. This is sensor to controller. This is controller to the actuator. And packet losses follow a Bernoulli distribution, P equal to 0.3. And to update the ergodic behavior, always we are doing Monte Carlo, 1000 iterations. Don't forget that. We do the Monte Carlo and we average them out. Goes without saying, because all this is stochastic. Okay? So, the augmented state vector, remember we talked about it, since output is alone is measured, yk, see that? So here is yk, and then the augmented state we are taking uk minus 1, uk minus 2. So the dimension of this vector is 3 by 1. And we are using tangent hyperbolic and a polynomial activation function. Okay, and here the critique uses 6th order polynomial. Okay, and it was generated using the gradient of the critique. And here is the alpha C, alpha V, alpha U. Okay, simulation was run for 20 seconds. And first 10 seconds, exploration noise was mean 0 variance. This is mainly to create persistency of excitation. Okay, so performance of the static feedback controller, static. And then if I'm using static controller, it can stabilize it without packet losses and delays. The minute I use the packet losses in the system, things blow up. Here is the stochastic controller. Using our approach, it converges, the critique parameters converge, the control input converges. Okay. And you can see that this is the heuristic. So I want to show you the heuristic. So we use the HTP. The HTP would converge when we are using 100 times per sample. It blows up when 10 times per sample. Okay? So that's your conclusion. I think that's my last slide. Any questions here? This is infinite horizon. Any questions?
Sir, if the C is not inverted.
Huh?
If the C is not inverted.
Then you can do it. You can use it. You have to take that pseudo inverse. You could use the pseudo inverse, but I'm just saying that you have to have the C that is inverted. Well, you cannot, because it's not observable. You cannot use it. So you have to meet the observability criteria to use that. That's where that C is going to play a role, right? Remember I said if it's not observable, you can actually modify the location so you get a C matrix. Yeah. That's right. Okay, any other questions, guys? Any other questions?
Sir, invertibility of the C is why it is required. In that case, if you are using pseudo inverse, so in that case.
So pseudo inverse is not always, you probably know there's a left and the right. So there are reasons why, if you can get a pure invertibility, it's good. But you don't need invertibility, you can use still the pseudo inverse. But what happens is we have seen in some cases, it's a problem. In some examples, it caused some problem. That's why I said. But you can get away with pseudo inverse.
No, the purpose is to get X from the Y.
Right. That's where you need it. Nowhere else. And also, when you build that capital F and G, you also probably need that C. Sometimes, that's another way, another place. So that's why I think it's an issue. What other questions? Any other questions, guys? All right, I think we may stop for tea, and And that would give you what I thought. I don't know whether you were here. I brought my laptop, so I wanted to show you. We will not record this because I'm going ahead by one lecture. I thought today there will be more students. But it looks like there are fewer. We will do the same thing maybe at the end, if at all. So I'll play some videos, I don't know whether I have all of them that I want to show you, but I'll try. I thought I would put everything in a folder and like you were asking the localization as well. Yeah, but I'll show you the autonomy part and we'll see if it's not there, then I'll try to, maybe on a different day we can bring that, okay? Yeah, we'll stop it. We don't need recording anymore. Thank you.